Okay, so this video is kind of sort of a review of everything we've done this unit, but basically other ways that they could ask you to do other questions, like different types of questions, based on what you know about like your understanding of function relationships. So maybe I've asked you these in the past, maybe you've seen them in the homework, maybe you haven't, but these are some pretty common concepts on the AP exam, or just in general that you could, like an extension of function relationships that maybe we've covered, maybe we haven't, but just in case, I want to make sure we go over a handful of these topics real quick today. So it's very common for them to give you f prime, like the graph of f prime, and use that to determine properties on f, okay? So in this problem, given f prime shown to the left, determine the locations of the relative minimums and maximums of f. Okay, well, a relative minimum or maximum occurs under two conditions. Well, I say two conditions. This could occur when f prime of x is equal to 0 or undefined and changes signs. Okay, that's one of our properties of relative minimums and maximums. So let's see, is there a place where f prime is equal to 0? Well, yes, absolutely. Here, there's a location, and then also right here. Okay, so these are our critical numbers, -1, and I'm going to say this is maybe supposed to be at +2, but who knows? Okay, 2-ish. Okay, so those are our critical numbers. For them to be a relative min or a max, though, my derivative also must change sign. Oh, I forgot to specify. Is there any place where this derivative is undefined? This looks like a nice, pretty polynomial curve. There's not a place where the function is, or the derivative is undefined, so we're good there. So at -1, my derivative changes from positive to negative, but at this 2-ish number, my derivative was negative, becomes 0 here, but then goes back to negative. Okay, so my derivative does not change sign over this number right here, but it does here. So at x equals -1, locates a relative. Now my derivative changed from positive to negative, so this is going to be a relative maximum because f prime of x, well actually f prime of -1 equals 0, and f prime changes from positive to negative. Essentially, we used the what test, amigos? Anyone? Anyone? This is our first derivative test. Okay, make sense? Excellent. All right, moving on. So find a missing constant k in an equation. Ooh, this is a very common one. Given f of x is equal to 3x squared plus k over x has an inflection point when x equals 1, find the value of k. So when I read this right here, I know in order for me to have a point of inflection, my second derivative of x is equal to 0 or is undefined, and okay, f double prime changes sign. Okay, just up here is not enough information. It has to be both for you to have a point of inflection. So because I know I need to look at my second derivative, let's go there. So f of x is equal to 3x squared plus k over x is the same thing as k times x to -1. I just rewrite it like that for the sake of taking the derivative. So then f prime of x is going to be 6x minus kx to -2. That's just my first derivative. I'm really looking for my second derivative. So f double prime of x is equal to 6 plus 2k x to -3. Okay, now I know that I have a point of inflection, aka one of these two things is happening at x equals 1. Well, I know that the only way for my second derivative to be undefined, because this is the same thing as 6 plus 2k over x cubed, the only way for my second derivative to be undefined would be at 0. Okay, or at x equals 0, because then I have a 0 in the denominator. So that's, you know, nice and all, but that doesn't really help me solve for k because I can't plug in a 0 here. But what I can determine then is that when x is equal to 1, that means my second derivative is equal to 0, okay? Because if I plug in a 1 here, that doesn't make my second derivative undefined. It's going to make the only possibility then it would be that my second derivative would have to equal 0. So my second derivative of 1 is equal to 0. That's what I have concluded based on this statement up here and looking at my actual second derivative, okay? So that means 0 is equal to 6 plus 2k over 1 cubed. I go ahead and I plug in 1 into my second derivative, okay? Because I know when I plug in a 1, I'm supposed to get 0. So it means 0 is equal to 6 plus 2k. So that means I have negative 6 is equal to 2k. So k is equal to negative 3. Okay, so find a missing constant k. Found it. K is equal to negative 3. Okay. Let's see the next concept here. Determine the relative minimums and maximums or inflection points based on an equation f prime, or f double prime. So given f prime is equal to x plus 1, x minus 3, x, find the relative minimums and maximums, or actually where they are, because I can determine the x values. I can't determine the y values of these because I don't have the function itself. So find the x values of relative minimums and maximums. Okay, so in order for me to have a relative minimum or a maximum, again, we've talked about this, f prime is equal to 0 or undefined and changes signs. Okay, that has to occur. So this derivative is pretty easy to set equal to 0. We'll do that here in a second. Is there a place where this derivative would be undefined? This whole thing is a polynomial, so the answer to that question would be no. So we just really need to look at where this is equal to 0. So 0 is equal to x plus 1, x minus 3, and times x. So that means this is equal to 0 at x equals negative 1, 3, and 0. So now I need to basically create a chart at all the numbers around these 3 numbers. So I'm going to go from, I'm actually going to need a little bit more room here. I know, isn't this so nice that we can do this? I'm going to take advantage while I can. Okay, so negative infinity to negative 1. Negative 1 to 0, 0, 0 to 3, and then 3 to infinity. Okay, I need to know what is happening on my derivative. So let's look at f prime of negative 2. I know that this is equal to 0, 0, 0. Okay. F prime of negative 2. Oh, luckily this is all nice and factored for me, so I can just plug this into the factored version. So negative 2, so negative 2 plus 1 is going to be a negative. Negative 2 minus 3 is a negative, times another negative. That's going to be negative. Okay. I'm going to plug in f prime of negative 1/2. Negative 1/2 plus 1 is a positive. Negative 1/2 minus 3 is a negative. Times a negative. All in all, positive. Okay. Let's plug in f prime of 1. So f prime of 1 would be positive. Like 1 plus 1 is positive. 1 minus 3 is negative. And then 1 times 1, or times 1 is positive. So that would be a negative. Okay, so I have negative, positive, negative, and I need to check one more interval here. So if I plug in f prime of 4, 4 plus 1 is a positive. 4 minus 3 is a positive. Times 4 is positive. So this is positive. Okay, so let me move that down. There we go. I know that my first derivative changed from negative to positive, and then positive to negative, negative to positive. So here I have a relative min, I have a relative max, relative min. So in this case, when they want to find the x values, so f has a relative minimum at x equals -1 and at 3, because f prime of -1 and f prime of 3 equals 0. Actually, what you can do instead of the word and right here, they're all equal to 0. And f prime changes from negative to positive. Sorry, ran out of room there. And then f has a relative max, x equals 0, because f prime of 0 equals 0. F prime changes from positive to negative. Okay, so not only do we have to specify where they're located, we need to know how we know that they were critical numbers in the first place. That's this piece, and then how you know which one's which, relative min, relative max. Okay, so let's say we had f double prime was 3x cubed minus x. Find the inflection points. Inflection points occur where f double prime of x is equal to 0 or undefined and changes signs. That must be true. So let's check. So I already have, oh, look at that. I already have the second derivative. So f double prime of x is 3x cubed minus x. This is a, it is a polynomial. I almost called it a quadratic. This is a cubic function, so I know it's continuous, so there's not a place where it's undefined. I don't have to worry about that. So I am going to set that to 0, though, so then I can factor out x. I'm left with 3x squared minus 1 as my, let's see, my solutions here. So x is equal to 0, and this is going to be x squared is equal to 1/3, so x, is equal to plus and minus root 1/3. You can rationalize that if you want to. I think you guys know how I feel about rationalization at this point. It's so irrational. That was funny. I laughed. Okay, let's see. So let's make a chart. So we're going to go from negative infinity to negative root 1/3. Negative root 1/3. I am going to run out of room. Let's see. Negative root 1/3 to 0, 0, 0 to positive root 1/3, positive root 1/3, positive root 1/3 to infinity. Okay. I know that my second derivative is equal to 0 here, here, and here. So I just need to find out what is happening on these 4 intervals. Okay. So I'm going to plug in numbers into my second derivative. Okay. Let's check f double prime of negative square root of 1/3. I have no idea what the square root of 1/3 is, but I know that it's pretty small. Let's just go with, it's got to be less than 1. So plug in -1 here. If I plug in a -1, I'm going to use my factored version. Okay. Negative times a positive would be a negative. Okay. Negative root 1/3. Ooh. I'm going to pick another small number, and actually it doesn't really matter what number I pick, because let's think about this. I mean, it does matter. It's got to be a negative number. But no matter what negative number I plug in, okay, this is going to make that negative. This, well, x squared. So let's say I plugged in like the square root of 1/4, okay, which is 1/2, right? Because that would be smaller or closer to 0 than what I have. Okay, 3 times that minus 1 is going to be a, oh man, of course I'm having a hard time doing this math in my head. Hang on a second. All right, so had to take a step back for a second because my notes from last year are apparently wrong. That's why I was getting confused. Okay, so yeah, you can plug in -1/2 right here. So -1/2, again, that would all be negative, but this right here, so 1/2 squared, yes, that's positive 1/4 times 3, 3/4 minus 1. So that's negative. Negative times a negative. So f double prime of negative 1/2 is positive. Okay. I could do f double prime of positive 1/2 now on this side. This would be positive. I already know that this would be a negative, so positive times a negative would be negative. And then, I don't know, let's go with f double prime of 1. And positive 3 times 1 squared minus 1, also positive, so this is positive. Okay, so I have points of inflection at, I'm going to clean this up just a smidge. OCD's come into play. Let's see, so I have, find the inflection point. So F has inflection points at x equals plus and minus root 1/3, comma 0. This is understood that it's both positive and negative root 1/3 because f double prime is equal to 0 and changes sign. Now, I have a feeling the reason why this question was brought up on here is because there are a lot of occurrences where you make this chart. I'm trying to think of an example off the top of my head, but I'm struggling at the moment. So there's going to be times where you make this whole chart right here, okay? And you're going to end up with something where it's like a negative here, positive, positive, okay? Where it's not going to change over all of the points, but it will change at some of them, okay? That is their way of trying to trick you. You have to plug the numbers into the chart. So just because your second derivative is equal to 0 or undefined, that's not enough to justify an inflection point. You have to also check to make sure that it changes signs. It did for all of these here. Pure coincidence. It won't always do that. You need to make sure that you're going back and checking. Okay? All right, moving on. Sketch a curve based on an equation. Oh my gosh, it's one of our favorites. It's at least my favorite. Okay, let's start from the very beginning. I'm going to move this up, give myself a little bit more space here. Let's see. We're going to have, let's start with our x-intercepts. X-intercepts. That's when my function is equal to 0. So 3x to the 1/3 minus x. This is kind of an odd one to factor, but that's okay. I'm going to just go ahead and set that equal to 0 and take an x out of both of these. So 0 equals x, 3, x negative 2/3 minus 1. Remember, if I take an x out of both of these, okay, you subtract a full 1. So 1/3 minus 1 is negative 2/3. Okay, so this, I already know x is equal to 0, but then I have 3x, actually let me go ahead and write that as 3 over x to the 2/3 equals 1, because you would set this whole thing equal to 0. So then 3 equals x to the 2/3, so then raise that to the 3/2. So x, so 3 to the 3/2, so 3 cubed is 27 over, so to the second, so square root of 27 equals x. You could leave it at that, or you can leave it as x equals 3 root 3. Okay, so I have, oh, and that's going to be plus and minus. Well, it's supposed to be plus and minus. However, looking at my interval here, I'm only going from -1 to 8. I only want to keep the positive. So my x-intercepts are going to be at 0, 0, and at positive 3 root 3, comma 0. Okay, those are my x-intercepts. Let's go to my y-intercepts, and that's going to be where my x value is equal to 0. Oh wait, haha, that's super easy because I actually already have that right here. My y-intercept is also one of my x-intercepts, so 0, 0. Easy peasy. Okay, so then let's see. What else do we need to do here? Oh, and behavior asymptotes and vertical asymptotes. We are supposed to check for those. It's not a rational function here, so it's not a polynomial because you have this 1/3 right here, but it's also not a rational. So we're not going to have there's no asymptotes here. If this had been a negative number right here, which would kick x to the denominator, then we would have a place where we would have a vertical asymptote. But there's not a number that I can't plug in for x here, nor is there a horizontal asymptote. So we can just specify no vertical asymptotes and behavior asymptotes. You don't have to write out that part out, but I like to write it out to make sure that I check off all the things that I need to look at. Okay, so now I need to look for changes in increasing and decreasing. So I need to look at my first derivative. So f of x was 3x to the 1/3 minus x. So that means f prime of x is going to be x to the negative 2/3 minus 1. So I need to set this equal to 0. 0 equals x to the negative 2/3 minus 1. I also need to check for where it's undefined, for my derivatives undefined. So then, I know this is kind of tricky for some folks. I'm going to move the 1 over. 1 equals 1 over x to the 2/3. Okay, cross multiply. X to the 2/3 is equal to 1. That's just x equals plus or minus 1. Because if you take the square root of both sides, you're going to have the plus and minus. Cubing it is still just going to be a 1, but it's going to be plus and minus 1 here. Okay, and then I want to know, so this is where f prime of x is equal to 0. F prime of x is going to be undefined when x is equal to 0, because this is in the denominator right here, and that would be a problem. Okay, so I've got critical numbers at plus and minus 1 and at 0. Now granted, negative 1 is on the endpoint of my graph, so not a big deal. It's just that normally we would probably check the other side of negative 1. Now we don't have to because they gave us closed interval. How nice of them. Okay, so when we make our chart here in a little bit, we'll put those in there for increasing, decreasing, all that good stuff. Now we need to look at our second derivative. So negative 2/3 x to the negative 5/3 is our second derivative. I look to see where this is equal to 0. So 0 equals, I'm going to go ahead and write that as negative 2 over 3 x to the 5/3. There is not a place where this is equal to 0, I don't believe, because even if I cross multiply to solve this bad boy here, I'm just going to get 0 equals negative 2, so this is going to have no solution. So there's not a place where it's not equal to 0, but is there a place where it's undefined? Absolutely. Yet again, it's undefined when x is equal to 0, which is the same place that it was undefined on the derivative. Okay, so if that's the case, this number, not only is it a critical number, so it's a possible relative min or max, but this now is a possible point of inflection. In order to check for that, though, I have to plug it into my chart and figure out, does my second derivative change sign? Okay, I have to check for that. I can't skip that. Okay, so all the numbers that we have, so we've got, well, we started at negative 1 because that is where our interval, we wanted the graph from negative 1 to 8. So let's see, I have a negative 1, 0, plus and minus 1. Oh, I have 0. Okay, so from negative 1 to 0, nope, 0. Talk about what's happening at 0. Go from 0 to 1, talk about 1, and then 1 to 8. And we're going to stop at 8. Okay, so we've got f prime, double prime. Boop. Okay, so we know that at 0, the derivatives were both the first and second derivatives were undefined. So undefined, okay. At positive 1, that was where my first derivative was equal to a 0, okay. Technically, that was also true at negative 1, but negative 1 is on my end, is on the end right here. So I don't actually have to check for that because I can't see what's relative min or max because it's an endpoint. So it wouldn't be either one anyway. Okay. So now I just need to look at intervals of increasing and decreasing. And then concave up and concave down. So, oh, and I already know that this coordinate is also 0 because of my x and y intercept. Okay, so let's plug in f prime of -1/2, f double prime of -1/2, f prime of 1/2. So let's see here. You're going to plug that in up here. So -1/2 to the -2/3. So let's see. I need some more. Oh, here, right here. F prime of -1/2 is going to be 1 over -1/2 to the 2/3. Okay. Usually if you do one of these, it kind of like jogs your memory here. It makes it a little bit easier to figure out. Oh, -1. So -1/2. Okay, so -1/2 to the 2/3. So -1/2 squared is going to be positive 1/4, positive 1/4. But then the cube root of that, I don't know, but I'm pretty sure. Let's see, 1 over 1 over 4 cube root -1. Basically, I just need to know if this is positive or negative. Oh, that is so gross. Let me think about this. Cube root of 1/4 is going to be pretty small. It's going to be less than 1. 1 over a number that's less than 1, since you're in the fraction here, it's going to flip it over and make it a number that's bigger than 1. So this is going to be positive. I'm almost positive. Let me double check that. Let me refer to notes from last year and yeah, we're good. Positive. Okay. I'm going to plug in -1/2 into my second derivative, f double prime of -1/2. So -2 over 3 times -1/2 to the 5. This is a little bit easier to figure out because there's not that extra -1 off the side, but also because if you have a negative to an odd power and an odd root underneath, this whole thing will stay negative. Still times the negative, but then like you have a negative divided by negative, so it's also going to be positive. So this one is positive. Whew, that's better. Okay. Oh, but now we have to plug in. Let's see. Let's go with, well, actually, now that those are both positive, I know that my function is increasing and concave up. Boom, done. Okay. And then I'm just going to, I mean, you can plug the numbers in here, but I'm going to kind of cheat for a bit and tell you that this is negative. This is also negative. Okay, when you plug it in, if you plug in a 0 into your second derivative, you get 0. So actually, oh, sorry, my bad. Not 0. I plugged in this number. I don't want to plug in that. When you plug in a 1 into your second derivative, you get a negative. So then that automatically guarantees that you have a relative max here by the second derivative test. And then, let's see here. Ooh, but that would be, that doesn't make sense. Because if that's a negative, that can't be a relative. Because it would have to change from positive to negative. All right, Murphy's going to have to pause for a second and figure out where she went wrong. Hang on. Okay, I found it. I tried to cheat and just give you what I had from last year. That was apparently a somewhat bad idea because my notes are wrong. Poor kids last year. Somehow they didn't catch that. But you know what? It's all good. They did just fine. It happens sometimes. Let's see. So positive, negative, and then from here, this one would be negative, and this one would still be negative as well. Fairly confident on that. This means my graph is going to be increasing but concave down, and my graph is going to be decreasing and concave down. Okay. To find out my actual location of my relative max, I need to plug that into my function. Plug that 1 into my function. F of 1 would be 3 times 1, so 2. Okay, so if I were to graph this lovely thing here, using all of the knowledge that I have pretty confidently confirmed at this point, from -1 to 8, we don't need to, I have a little too much there. Okay, so, because it's an endpoint, I probably need to check out what my y values are. So I need f of -1. I already know that f of 1 was 2. I need f of 8. So 3 times -1 to the 1/3 minus 1. This is going to be -3 minus 1, so -4. And then I think, my notes from last year say -2. Mervin, oh my God. I got this, you guys. Promise. I promise. This was supposed to be minus -1. There we go. That's -2. Okay. That one I'm pretty sure is still 2. And then 3 times 8 to the 1/3 minus 8. It's a minus x, not just a -1. That's what I messed up a minute ago. Cube root of 8 is 2 times 3 is 6 minus 8 is -2. Okay, so we've got a -1, -1, -2. At 0, we were at 0, over 1, up 2, and then at 8, 1, 2, 3, 4, 5, 6, 7, 8, all the way down to -2. Okay, for this piece right here, from -1 to 0, my function is increasing and concave up. From 0 to 1, it's still increasing, but now concave down. I have a relative max at 2, and then my function is decreasing and concave down. Oh, and it crosses at that 3 root, you know, it's going to cross in there somewhere. There you go. So that's what your graph looks like. Ta-da! How lovely is that? Not too shabby. Sorry for the oopses in there. But you know, it's just like being in class. I screw up in class all the time. Why not do that in the video? You know, because I can't like go back and rewind this thing and fix it. So, you know, it is what it is. Let's keep going. Sketch a curve based on a description. So, given h of x is continuous on the interval, if I see this, that means there are no removable discontinuities, meaning like a hole that's like above it or something, or vertical asymptotes. Okay, none of those. From -1 to 4, okay, so, it's only continuous from -1 to 4. All right. And satisfies the following criteria. That's all we want. Okay, from -1 to 4. So h of -1 is 2. So -1, 2. H prime of 2 is undefined, but my function is continuous, so I know that's not a vertical asymptote. H prime is negative, so H prime is negative, so H is decreasing, H double prime is positive, so decrease and concave up from -1 to 2, and then H prime is undefined at 2, H prime of x is greater than 0, so it's so H is increasing and concave down from 2 to 4. So I have -1 is 2. I have my function is decreasing concave up until 2, and then it changes from increasing to concave down. And I just know that the derivative doesn't exist at 2, but I don't, or is it's undefined. So, but my function is continuous, so I'm going to say there's a sharp turn, so decreasing and concave up, but then increasing concave down. Boom. That's one example. We wanted to stop this at 4. I don't want the arrow then. I want to stop this at 3, 4, boom. There we go. This probably, honestly, on this graph right here for this piece, I would recommend that you try to make that look a little bit more curved. If there's any doubt in my mind that it's not like it's an actual curve and it looks somewhat linear, then I would say, hey, you didn't make that concave up enough. So make sure it's very distinct concavity there. Okay, let's do one more. Sketch curve based on a table. Oh, luckily they already had the whole thing filled out for you. Okay, so this is basically word for word a former AP question. I can already tell by the formatting of it. So let's sketch the curve. Oh, that sketching is is part B. Okay, for problems like this, it's even though there's a part A up here above it, I mean, it could be helpful to do part B first, to go ahead and sketch the graph and then answer the question. It's totally up to you though. Everybody has their own personal preference. Sometimes it's easier to answer the questions about the graph if you know what the graph looks like. Now, granted, if you drew the graph incorrectly, that could be a problem, but hopefully that's not the case. So, sketch the graph, the given characteristics. At x equals 0, my f of x is -1, so 0, -1. At 1, I'm at 0, so 1, 0. At 2, it's at 2, so 2, 2. At 3, we're back at 0. And I don't know what's happening after that. Okay, so between 0 and 1, I know that my function is negative, okay, and my derivative is positive, which means my function is increasing, but my second derivative is negative, so it's concave down. So it's increasing, concave down, but still negative, so increasing and concave down. From 1 to 2, I'm now above the x-axis, positive, positive, so it's increasing, concave up. Okay, so increasing, concave up to this point right here. My second derivative, my first and second derivative doesn't exist at 2, so that's potentially going to be a cusp right there, I would say. Yeah, it's not going to be an asymptote because of this number, or this word right here, so I know I don't have an asymptote. And then I've got from 2 to 3, I'm still above the x-axis, negative, negative, so decreasing, concave down. I meant to put that up there, but you know what I mean. So decreasing, concave down. Okay, and then negative, negative, positive, so below the x-axis, decreasing, concave up. And I don't know the y value at 4, and that's okay, so I'm just going to go to that. Okay, and leave it open-ended here, because I don't know, well, it's on the interval from 0 to 4. I'm going to put an open circle at 4, because of this thing right here. I don't know what's happening at 4. Okay, so that's my sketch. So let's go back to part A. From 0 to 4, find all the values for which f has a relative extremum. Okay, when we say relative extremum, f prime of x needs to do two things. It needs to be 0 or undefined and change signs. So determine whether it has a relative min or max at each of these values, justify your answer. So let's start with 1. Oh, look, my first derivative is equal to 0 at 1, but my sign does not change on either side of 1. So that is neither a relative min or a relative max. So no relative extrema there. Okay, so I go to 2. My first derivative does not exist. Oh, but my derivative does change signs. So then, because my derivative changes from positive to negative, that tells me I have a relative max. So f has a relative max at x equals 2 because f prime of 2 does not exist and f prime changes from positive to negative. Let's check the last number at -3. Or at 3, my derivative is equal to -3, so that's not even a critical number. So my only two critical numbers were 1 and 2. My sign did not change at 1, but it did change over 2 on my derivative. Therefore, I have a relative maximum at 2. Okay? So that is a quick recap. I say quick. Oh my gosh, that was a longer video than I intended, but it's about a little bit less than what it would have been if we were having this discussion in class. So there you go. Different ways of asking you how to look at function relationships. This isn't necessarily all of the ways that we could ask them. It's just a wide variety of the ones that we could.